This meeting is being recorded.
Okay. Yeah. So, hi and welcome to the Python Maven. Let's call it Python Maven. This is the Code Maven YouTube channel, and we are organizing these meetings in the Code Maven's group, but sort of it has three separate sessions, and this is going to be the Python specific one. My name is Gabor Sabo. I usually teach Python and Rust and help companies introduce testing, and I also like to organize these events and allow people to share their knowledge with each other. You're welcome. I'm really happy that you're here in this session listening. As I mentioned earlier, you're welcome to comment or use the chat and ask questions. And if you're just watching the video recorded on YouTube, then please remember to like the video and follow the channel. And let's welcome Haki now and let him introduce yourself and give the presentation. So thank you for accepting the invitation.
Thank you, Gabo. First of all, I like the fact that we have this intimate group that we can freely talk. I actually encourage you to consider opening the mics because I think we can actually have a conversation throughout the presentation. I like to give interactive presentation. Your call, you're the boss.
Okay.
And just a quick introduction about the subject and about myself. So we are going to talk about how to make your backend roar. And I want to start by apologizing for the tacky headline. But unfortunately, these types of tacky headlines do work, believe it or not. So my name is Haki Benita. I'm a software developer and a technical lead. I'm currently leading a team of developers working on a very large ticketing platform in Israel, serving about 1.5 million unique paying users every month. And I also like to write and talk about Python performance and databases. And you can find my stuff on my website. So today we are going to talk about some lesser known features of indexes, and we're going to try and understand how they work and when we can and should use them. To do that, we are going to build a URL shortener together, and we're going to do it in Django. I would say that since this is a talk about Python, I'm going to use Django and the Django ORM, but the concepts that I'm going to describe are not specific to Django, and they're not specific to Postgres. Heck, they're not even specific to Python. But this is a good environment to explain the concepts with. So what is a URL shortener? You probably know about other types of URL shorteners. You have Bitly, you have the late GoogGL, BufferLI, and so on. Basically, URL shortener is a system that provides a short URL that redirects to a longer URL. Now, why would you want to do that? First, if you're operating in text-constrained environments like SMS messages or tweets, you might want to share a very large link. So you want to make it shorter so it consumes less space. This is where short URLs can be handy. Another nice features of URL shortener that whenever someone clicks the short URL, the URL shortener redirects to the long URL and keeps a track of how many people click that link. So if you have something like a campaign that you want to launch and you want to keep track of how many people clicked your link, this is what you would use a URL shortener for. So to build our URL shortener in Django, we're going to start with this very, very simple model. We are calling the model short URL. We have an ID column, which is the primary key. It's just an auto-incrementing integer field. We have the key. That's a unique short piece of text that uniquely identifies our short URL. This is the short key at the end of the short URL. We then have the URL, which is the long URL we want to redirect to. We also want to keep track of when the URL was created. We do that using the created at column. And finally, we want to keep track of how many users click the link. And we do that with the hits column at the bottom. So for our demonstration, so we actually have something to work with. I loaded 1 million short URLs into the table, okay? Now, this is not a lot, but we are going to see some performance gains with just 1 million rows, okay? So this talk is about Python, but it's essentially about SQL. So in Django, if you want to get the SQL generated by Django for a given query set, you can do that by accessing the query set.query and print it. In this case, I'm doing short URL filter on a specific key .query, and I can actually get Django to print the SQL that it generated for this query set, right? So after viewing the query set, it's also very interesting to see how the database is planning to execute my query, right? So I can do that by executing the function explain. This translates into an explain query command in SQL, and what I get in return is not the result of the query, but the execution plan, which is how the database is planning to execute my query. Now, when we just use explain, the database doesn't actually execute the query, it just produces a plan. Sometimes, especially when we're benchmarking and we're trying to improve performance, it can be useful to produce the execution plan, but also have the database execute this query and return some useful execution data. For that, we can use a slightly different variation of the explain command, which is explain analyze. In Django, you can do that by using explain analyze true. In SQL, Postgres specifically, you can do explain analyze on, timing on in parentheses, following by the query. And then you get some additional information about the execution plan. First, because the database actually executed the query, you can see at the bottom that we get how long it took the database to produce an execution plan. In this case, that would be 0.140 milliseconds. And I also get how long it took the database to execute the query from start to end. In this case, that would be 0.046, okay? Now, in addition to the timing, I'm also getting a very, very interesting piece of information inside the execution plan, okay? What I get is the estimated cost and the actual cost that the database encountered while executing the query. So discussing the cost-based optimizer is slightly outside the scope of this talk. I would just say that comparing the expected cost to the actual cost is a very useful measure to try and identify bad execution plans. Finally, another way of viewing queries is to turn on the logger for the database backend in Django. This way, whenever Django executes a query, it logs the SQL that was produced by the ORM. So, to actually start discussing some indexing techniques, we need to start implementing some, business processes. So let's start with the most basic thing that a URL shortener actually does, and that's look up the URL to redirect to by a key. So a user uses one of our short URLs, we get the unique key, and we need to find the long URL to redirect to, okay? This is like the bread and butter of this system. So if we want to implement this very, very simple function, we can do something like that, def resolve, okay? That's the name of the function. We want to resolve a key to a URL. We accept a key, and then we execute this simple query to just get a short URL for this key. If we don't find anything, we return none. Otherwise, we return the URL to redirect to, okay? Now, we want to look at the SQL that Django generated for this function, right? So we execute this function on some random key with SQL logging turned on, and we can see the query right here. Now, if you look at this query, it looks like Django basically fetch everything from the short URL table for the key that we asked for, right? So like start from short URL where key equals something. If we want to look at how Postgres is actually executing this query, we can use the explain command. And what we get is that Postgres is planning to use an index scan on the index we have on the key column. Okay? Now, to understand what exactly it means an index scan, let's take a second to talk about B-tree index. So B-tree index is like the king of all indexes. This is the default index in most database engines. If you're not sure what type of index you're using, you're probably using a B-tree index, okay? So to understand how a B-tree index works, let's start by building one. So imagine you have these values 1 through 9, and you want to create a B-tree index on them. You start by sorting the values and storing them in leaf blocks. You can see the leaf blocks at the bottom. They are sorted from left to right. We have 1, 2, 3, all the way through 9. Now, every entry in the leaf blocks contains a list of TIDs. These are pointers to rows in the table that store rows with these values, okay? Now, above the leaves, we have branches and root block that acts as a directory to these leaf blocks. So let's see how this works. Let's imagine that we want to look.
Sorry,
Yeah.
someone says that it doesn't see the slides, so I just wanted to, and I'm sure if the other people do see the slides. So if I asked it in the chat, but no one answered. So I hope that okay, so some other people see it. So my recommendation is to Eduardo to turn maybe on and off maybe exit Zoom and enter Zoom again. Sorry for the interruption.
Okay, no problem. Yeah. Okay. Okay, so let's try to search for the value 5 in the B-tree index that we just built. So we start with the root block, and we start scanning from left to right. So 5 is larger than 3, so we skip the first entry. 3 is between 3 and 7. 5 is between 3 and 7. So we follow this pointer to the middle leaf block. We then start scanning the leaf block from left to right. The first value is 4. It's not a match. The next value is 5. That's a match. And now we can follow the pointers from this leaf block to the rows in the table. We can read the rows and do whatever we need to do with these rows, okay? Now, let's go back to our query, okay? 1 second. Yeah, let's go back to our query. Remember that we said that Django generated this query, and this query is fetching everything, right? Basically select star from short URL. But in fact, if you think about it, we don't actually care about all these fields, right? We only care about the URL. I mean, when I'm looking to resolve a key to a URL for the purpose of redirecting, I don't care when it was created. I don't care about the ID. I already have the key, right? And I don't care about the hit counter at this point, right? So I don't care about all these fields. So one thing that we can do is, instead of fetching all of these fields, how about if we just fetch what we actually need, right? So in Django, we can do that by adding values list URL. Now, the function is slightly different, but if we look at the SQL generated by this function, we can see that now, instead of fetching all the columns in the row, we just fetch the URL. So this is exactly what we need. If we look at this execution plan, once again, for this query, we can see that, again, Postgres is using an index scan on the unique index that we have on the key, right? So now, once we found a matching row, we can follow the pointer to the table. We can get the URL from the table. So if you imagine the amount of disk reads I need to do to satisfy this query, I'm starting by reading the root block, right? So that's one read. Then I need to follow the branch all the way to the leaf. Let's say that we have just, root block and then directly to the leaf. So reading the leaf is another read. And then we need to follow the link from the leaf block to read the row from the table. So this is a unique column. So we have at most one row. So that's another read. So basically we did 3 random reads to satisfy this query, right? Now, this query is executed a lot. This is basically what our system is doing, right? It's getting keys and resolving them to URLs to redirect, right? Now, we already established that all we care about in this specific scenario is just the URL. I don't care about anything else. I care just about the URL. So what if, and stay with me, this is mind-blowing, what if instead of going to the table to get the URL, what if I could include the URL in the leaf block, in the index? This way, when I found a matching entry in the leaf block, I would have the URL just sitting there, right? So this mind-blowing idea is called inclusive index, okay? In other databases, it's called covering index or inclusive indexes. And what it allows us to do, it allows us to store additional information in the leaf block. So if we want to use an inclusive index in Django, we can add the include argument to the unique constraint. Now look, the key is indexed. The URL is not indexed. It's just included in the leaf block, okay? Now, if we generate a migration, we apply it, and we try the query again, you can see that once again, Postgres is using our index, our unique index on the key, but there is a very, very subtle difference here. If you notice, previously we had an index scan using our unique index. This time we have an index-only scan. This means that Postgres was able to satisfy the query without accessing the table. All the data that it needs was already in the leaf block. So if we once again imagine how many reads we need to do to satisfy this query using the inclusive index, we read the root block, we follow the pointer all the way down to the leaf block, and now instead of going to the table to read the URL, we have the URL right there in the leaf block. So we only need to read 2 blocks from disk, okay? The way to identify this is by the operator on the index-only scan, right? So we have an index scan and we have an index-only scan. So, quick recap about inclusive indexes. As I mentioned, in other databases, they are sometimes called covering indexes, and they allow us to fulfill queries without accessing the table. However, you should use them with caution, because if you think about it, we're basically duplicating data from the table to the index, okay? So if you have a very big piece of like information, like URL can be very, very big. So basically I'm now storing the URL twice. So the index could get very, very big. I'm actually not a big fan of inclusive indexes, but I can think of 2 scenarios where it might be a good idea. First, if you have very wide tables, imagine like data warehouse type of tables, denormalized tables, and you have a very predefined set of queries that are executed very, very often on a very, very small subset of columns, you can consider using an inclusive index. And also, I personally found that non-unique composite indexes can be good candidates for inclusive indexes. That is, indexes on multiple columns that are not used to enforce a unique constraint. Sometimes they can benefit from switching to just a composite index to an inclusive index, okay? Questions so far before we move on to the next use case? Okay, if you have any questions, feel free. Let's move on to the next use case. So now we want to find unused keys, right? We have this business question. We want to know how many short URLs we have with no hits at all, okay? We have 0 hits. So we start by implementing this very, very simple function. We call it find unused indexes, and it returns a query set where with short URLs where hits equals 0. Once again, if we want to see what the query looks like, we can print the result of query. We can see that it returns like star from short URL where hits equals 0. Once again, through the process, we produce an execution plan. This time we can see that Postgres is doing a sequential scan on short URL. A sequential scan is basically a full table scan. Postgres is just reading the table row by row, looking for rows where hits equal 0. We can see that the execution time at the bottom is 116 milliseconds. Let's say, for the sake of discussion, that this is very, very slow, and we want to try and improve that. So if you go to like 99% of developers at DBA, they will tell you, what's the problem, man? Just slap a B-tree on it, right? So we add a B-tree index on the hits column. We do that in Django using db index equals true. We generate a migration. We apply the migration. We once again produce the execution plan with analyze, and lo and behold, Postgres is using our index short URL hits IX. And as you can see, the execution time is very, very fast compared to before. So we're done, right? We can call it the day. We can go for lunch. We're happy. It's fast now. Stop. Let's take a second to talk about performance and what it actually means, okay? Because intuitively, when we talk about performance, we talk about speed, right? We want things to be very, very quick. But I think, or the way I view performance, is that we need to balance different types of resources. And I want to illustrate this with an example, okay? Let's say that you have this batch processing job running at night. Now, this batch processing job runs at the middle of the night where you have very, very little users, and it runs very, very fast. It takes like this batch processing job like 10 seconds to complete. You're so happy, it's so fast. However, this job consumes huge amounts of memory, huge amounts of CPU, and huge amounts of disk space, right? What if I told you that if we are willing to compromise, and instead of completing in 10 seconds, it takes a minute, right? It consumes very little memory, disk space, and CPU, right? I'm guessing that if you pay a lot of money for memory, you are willing to make this compromise, okay? I'll give you another example. Let's say that you have this background job running in the middle of the day, right? Now, this background job consumes a lot of CPU. So much CPU, in fact, that it starts to interfere with user traffic in the system. In this case, instead of optimizing for time, you might be optimizing for CPU, right? You're willing to compromise a few seconds, but you don't want the background job to consume a lot of CPU. So when we talk about performance, we talk about more than just speed. We're talking about how we can balance different resources in the system, usually depending on some type of context, time of day, the type of resource that we have available at this time, right? So remember that we slapped a B-tree on it, right? And it was very, very fast. But I'm not sure that it was like the most optimal thing that we could have done. So let's go to the database and see and check the size of the index we created to solve this teeny tiny problem, okay? So this index, right, is 7 megabytes, okay? So that's pretty big for this type of index. So our 7 megabytes index includes all the rows in the table, right? We just add a db index true, create a B-tree index on the column, so it contains all the 1 million rows in the table. But we actually don't care about all the rows in the table, right? Nobody asked us how many short URLs you have with less than 5 hits or more than 266 hits or exactly 1,000 hits. Nobody cares about that. We had a very specific question that we wanted to answer in regard to the hits. We wanted to find how many short URLs we have with exactly 0 hits. So what if, instead of indexing all the rows in the table, we could index just the portion of the rows, the part of the table that we actually care about, right? So this is once again, mind-blowing idea. And this is made possible with something called partial indexes. Partial indexes allows us to index just the part of the table that we actually care about. So going back to our Django model, right? First, we start by removing the DB index from the column definition. You should never use DB index regardless of this. And then instead of adding this default index on the column, we add a proper index, right? But we add a condition, okay? So what this does, it creates an index on the ID column with a condition where hits equals 0. This would cause Postgres to create an index just on the rows that satisfy this query, just on rows where hits equal 0, right? So we generate the migration, we apply the migration, and we try the query again. We produce an execution plan, and we can see that Postgres is using our index, right? We see an index scan using show URL unused part IX. This is the index we just created, okay? So Postgres is able to use the index we just created, the partial index, to satisfy this very specific query. We can also see that the query is very, very fast, even compared to the full index, right? But that wasn't the motivation here, right? This is not what we look to optimize. If we go back to the database and we look at the size of this index, look at that. The partial index is just 88 kilobytes in size, okay? Previously, the full index was 7 megabytes. The partial index is 88 kilobytes. So I did the math. Seriously, I opened Excel, I did the math. That's 99% smaller, okay? So that's a lot of space. Now, at this point, you're probably saying, come on, man, it's just 7 megabytes, who cares? But if you go back to your system and you have huge tables with hundreds and billions of rows, right? Check the size of your B-tree indexes. They can become huge. I've seen situations where the B-tree index was larger than the table, okay? And if you have a lot of indexes, it can grow out of control very, very quickly. So, as you may guess, I'm a very, very big fan of partial indexes. They produce smaller indexes, and I highly encourage you to use them whenever possible. One limitation of partial indexes is that the database can only use partial indexes when the query uses the exact same condition as the predicate in the index, right? The database is not even smart enough to do something like where hits equal 1 minus 1, okay? To this level, okay? So it's limited to queries that use the exact same condition. Usually it's fine because, you know, why would you do hits equal 1 minus 1? I don't know. I personally found that nullable columns are great candidates for partial indexes because in Postgres, for example, null values are indexed. And usually you don't want to use an index for is-null queries. So I found that whenever I have a nullable column with an index on it, I can benefit from making it a partial indexes. In fact, I wrote an entire article on how we save 20 gigabytes of unused disk space simply by identifying nullable columns with indexes and switching them to use partial index. Okay, so questions about partial indexes before we move on to the next use case? Gabor, you have a question? No,
Actually, there is a, sorry, actually, there is a question.
Is it a good idea to recalculate the hits and partial indexes? How frequently? Well, the nice thing about indexes and B-trees in general, that they are always in sync with the data in the table. It's actually part of the transaction. So when you, for example, increment the counter for the first time, the row would just disappear from the index, right? So I'm guessing that you're asking because you have some experience with like materialized views and stuff like that. So you don't actually have to maintain it actively. It's just maintained by the database. It's truly an amazing feature. You should definitely use that. Any more questions before we move on to a very exotic type of index in Postgres? Okay, great. So let's talk about another use case. So in the first use case, we wanted to resolve the key to a URL, right? This is the redirect action. This time, we want to do a reverse lookup. We want to ask how many keys we have pointing to this specific URL. So we want to search for keys by the URL. So we implement this very simple function called reverse lookup. It accepts a URL and returns a query set of short URLs, okay? So if we want to see what the query looks like, we use .query, and we can see select star from short URL where URL equals something, okay? If we produce an execution plan, we can see that the database is doing a sequential scan on the short URL table. That is scanning the entire table, sifting row by row, finding matches for our query. And we can see that it's relatively slow, right? It's like 105 milliseconds. So compared to the indexed queries that we saw before, that's pretty slow, right? So once again, 99% of the people would just say, "Come on, man, I'm hungry. Let's order some food. Just slap a B-tree on it." So this is what we do, right? We start by adding a B-tree on the URL, right? We generate and apply the migration. Now we execute the exact same query again. And we can see that now Postgres is using the index that we just created. We can see an index scan using the index on the URL column. And also, it's very fast. Previously, it was like a 100 milliseconds. Now it's 0.1 milliseconds. So that's a very, very big and significant improvement. We can all see to launch and be very, very happy and satisfied with ourselves. But are we done? Do you think that we are done? Is there anything that we can optimize? Now, if you are paying attention throughout this presentation, you know that we can definitely do better than that. Let's go to the database and check the size of the index, okay? So the size of the index, okay, stay with me, 47 megabytes. If you remember in the previous use case, we had an index on all the hits. It was 7 megabytes. I told you it was large. This index on the same amount of rows is 47 megabytes. That's very, very big. And the reason that it's very, very big is that the URL is very, very big, right? The B-tree index holds the actual values in the leaf block. So if we are indexing a column with very large values, like URLs can be very, very big. So if we are indexing a column with very, very big values, these values are also present in the index, and the index can get very, very big. So previously, when we were indexing integers, it was 7 megabytes. Now we're indexing large pieces of text, URLs, and that's 47 megabytes, okay? So let's pause for a second, okay? I know that B-tree is like the magic for 90% of the use cases, but there are other types of indexes that we can use. So let's pause for a second and ask ourselves, what do we know about the URL, okay? So first of all, we know that URL is not unique, right? We can have multiple keys pointing to the same URL. We can have, for example, different campaigns with different short URLs pointing to the same URL. There's no restriction in the system. You can have many keys pointing to the same URL, so it's not unique. However, if we actually look at the data, we see that we don't have a lot of duplicate long URLs, right? Like, it's not likely that people will use the same short URL to point to the same URL. Like at the very least, they would have different UTM parameters for the same URL. So while it's not a restriction, you can have many keys pointing to the same URL. It's not likely. So we don't have a lot of duplicate values. So now I want to introduce you to what I call the ugly duckling of index types in Postgres, the hash index, okay? And to understand how a hash index works and why it's different from a B-tree index, let's start by actually building a hash index ourselves, okay? So imagine we have these values A, B, C, and D, and we want to index them using a hash index. So we start by applying a hash function on each value. So Postgres, in our example, it has different hash functions for different types. So you can see that we have hash for text, char, arrays, even JSON types, timestamps, and so on. In our case, we have just one character, so it uses hash char. If we actually apply this function on the values, we get the hash values. The next step is we want to divide these values into buckets. So we start by dividing them into two buckets. Basically, we apply modulo 2 on on the hash value, and then we assign each value to a bucket. So we can see that A goes to bucket 1, and B, C, and D goes to bucket 0. So this is our hash index, okay? So we have 3 hash values in bucket 0. Each hash value points to somewhere in the table, okay? Just like we had the TIDs in the B tree, we have the TIDs right here in the hash index. Now, if we want to use this hash index to find some value, we do the exact same thing, but the opposite, but the other way around, right? So if we want to search for the value B, for example, we apply a hash function on it, we get the hash value, we apply modulo number of buckets to get the bucket, in this case 0, and then we go to bucket 0 and we start scanning the pointers to find matching hash. Once we found a matching hash, we can take this 2, which is a pointer to a place in the table, and we can go scan this row and look for matching rows, okay? So this is how a hash index works in Postgres. Now, if we want to create a hash index in Django, we need to use the special hash index from Postgres contrib, okay? The reason for that is that hash index is not the default index type in Postgres, so we need to explicitly say we want a hash index, okay? So in this case, we are creating a hash index on the URL field, and the name of this index is going to be short URL HIX. I like to use a suffix that indicates the type of the index. So when I look at execution plans, I can quickly identify the type of the index. So I usually use IX for B-tree indexes, and then I use part IX for partial, HIX for hash indexes, and so on. You can come up with whatever convention you want. So we generate the migration, we apply the migration, and produce an execution plan, and we can see that Postgres is using our hash index, okay? Now, okay, first observation, this is very, very fast, okay? So you can see that 0.07 milliseconds, that's very, very fast, but that's not all. If we look at the size of our hash index compared to the B-tree index, we can see that the hash index is 30% smaller, okay? Trust me, I took a calculator, an old Casio, and I calculated the difference. It's 30% smaller, okay? That's very, very significant, okay? If we put all the data in a table, you can see that the hash index in this case was both faster and smaller. So that's a win-win all around, okay? Faster and smaller than the default B-tree index. Now, I did a little experiment, okay? So what I did was I created a hash index and a B-tree index on the key and on the URL, okay? You can see the chart right here. I have a hash index on the key, I have a hash index on the URL. I have a B-tree on the key, and I have a B-tree on the URL. And what I did is I started adding rows to the table, okay? You can see at the bottom axis, that's the number of rows. So I started adding rows into the table until I get to 1 million rows. Now, every time I added rows to the table, I took a snapshot of the sizes of the hash index, of all the indexes. And then I put all the data in this chart. And we can see some interesting things, okay? First of all, if you look at the red line, which is the B-tree on the URL, big piece of text. And the green line, which is the B tree on the key, the short piece of text. First of all, you can see that both of them grow basically linearly as I add more rows to the table, right? So we can see that like this linear line increasing, right? As I add more rows, the size of the index increases. We can also see that the red line, the B tree on the URL, is always larger than the B tree on the key, right? So the reason for that is that the URL is a big piece of text and the key is a short piece of text. This tells us that the size of the B tree is very much affected by the size of the column that it indexes. So a B tree on URL will be bigger than a B tree on key for the same amount of rows because a URL is bigger than a key. So that's about the B tree indexes. However, if we look at the hash indexes, that's the blue and the yellow lines. First of all, we can see that the size of the hash index, if I add more rows, is not affected by the size of the value because URL is big, key is small, but as I add more rows to the table, the size of the hash index is the same, okay? The second thing that I can see is that in this specific case, the hash index was consistently lower, smaller than the same index, the same B tree index on the same column, okay? So in this case, the hash index was always smaller. Another thing that we can see in this chart, that unlike the B tree index that grows linearly, the hash index grows in like steps, right? You can see the step and then it's flat, step, flat. So what's happening in a hash index is once we start adding rows to the hash index, and then we have some bucket, and this bucket starts to fill up. Now, when a bucket fills up, Postgres needs to split this bucket. Now, when the bucket is split, Postgres pre-allocates storage, disk space for this bucket. So the steps that you see is the bucket splits, where Postgres allocates additional storage to split the bucket, right? So this is why a hash index grows in steps. So hash index is ideal when we have very few duplicates in the rows that we want to index. And the reason for that is if we have lots of duplicates, the values will map to the same bucket and we won't get the benefit of a hash index. The reason that a hash index made sense in our case is that URL is mostly unique. It's almost unique, okay? It's not unique by definition, but there's not a lot of duplicates. We also saw that unlike a B tree index, hash index is not affected by the size of the values that it indexes. And the reason for that is that the hash index doesn't actually include the values, it includes hash values. Okay, this is why I can index very, very big values, big strings, with a relatively small index. Okay, as we saw, hash index under some circumstances can be both smaller and faster than a B tree index. And the reason that a lot of people are unfamiliar with a hash index is that prior to Postgres 10, which is already pretty old because we're now at Postgres 17, if you went to the documentation for hash index, there would be like this huge warning saying, beware, do not use hash indexes. They are not production ready. So a lot of developers became used to not using hash indexes. But starting at Postgres 10, you can definitely use hash indexes in production. They are segged, they are production ready. And as we saw, they can be very, very good under some circumstances. When talking about hash indexes, it is very important to also know the restrictions of hash indexes. First of all, hash index cannot be used to you can't create a unique hash index. And the reason that you can is that a hash index does not contain the actual values, just hash values. And technically, you can have multiple different values producing the exact same hash value. So you can create a unique hash index. However, okay, and that's the comment at the bottom, we can talk about it later if you want, you can enforce unique with a hash index using an exclusion constraint, okay? Next, we can have a composite hash index. We can have a hash index on multiple columns, okay? And we can use hash index for sorting and range searches because, once again, hash index does not contain the actual values, just the hash values, right? So I can use a hash index for things like, between, greater than, less than, and so on. Just equality. So, quick recap, just 4 more slides, I promise, okay? When to use indexes. So remember, indexes can make queries faster. We saw that in all of our examples. Using an index made the query faster. However, they're not free. They come at a cost. You need to maintain this index. And this index maintenance happens when you insert, when you update, and when you delete. So the more indexes you create, the faster your queries are, but the slower every other operation is. Okay. Another thing to consider, and this is often overlooked, indexes can be very, very big. They consume a lot of disk space. When you go back to your databases after this talk, please go do /di plus and look at the sizes of your index. I think that if you never looked at the sizes of your indexes, you're going to be very much surprised at what you're going to find. And finally, using an index is not always best. If you have a query that needs to access a large portion of the table, sometimes it doesn't make sense to use an index for that, okay? There's no magic number, but, keep that in mind. So we talked about index types and features. We talked about partial indexes, inclusive B-tree indexes, and we talked about hash index. We talked a little bit about how to evaluate performance. I don't know if you noticed, but throughout this presentation, we went through the same process over and over again. We start by executing some query with explain analyze to get the timing with no indexes. This is basically establishing a baseline, right? And then we start by experimenting with different types of indexes. So usually we start with a B tree. We take a measure of the time using explain analyze, and then we take the size of the index, we put it all in a nice table, we start experimenting, and once you have all the data organized like that, it's a lot easier to reach a decision on what is the best indexing approach for your specific use case. And also, and hopefully you remember that, indexes, performance is not just about speed. As we saw, we can get significant disk space reductions with a very small price of speed. Sometimes it makes sense to make this compromise. We also, throughout this talk, saw how to use explain, analyze, how to debug SQL in Django. We also saw a lot of execution plans. I don't know if you noticed, but if you've never seen execution plans before, hopefully when you go back to your system, you start doing explain analyze with some of the queries you run a lot, you get to actually understand what the database is doing. Now, in this talk, I talked only about inclusive indexes, partial indexes, and a hash index. But in fact, there are many, many different other types of indexes that are exotic and very, very cool. We have Bren indexes, we have function-based indexes, and we have a lot of different flavors of things that we can do. And you can check out this class, 3 hours packed with SQL magic for your benefit. And finally, check me out in all of these places. And I'm happy to take questions or discuss whatever you want.
Wow. Thank you. It's, yeah.
Hectic.
Yeah. This is not a question. Haki's article on hash indexes is truly excellent. I believe it remains one of the top search results for anyone looking for resources on hash indexes.
It's true. It's true. This is one of the top searches for hash indexing Postgres.
Yeah.
Yeah, I managed to catch this trend very, very early on.
Nice. Okay. Any comments, questions before we close this session? We know where to find you. We'll have the link. We can add the links to the post of the video as well, so people can find it easily. Any comments,
Okay.
questions? Apparently not.
Yeah, I want to thank you, Gabor, for hosting this meeting,
It was
this
excellent.
meetup.
Yeah, well, yeah. So thank you very much for this presentation. If anyone has questions, then we'll see how to find the Haki later on in this
Yeah.
on this slide, and then we'll put it under the video. Thank you for supporting us. Thank you for being here. Thank you very much to you to giving the presentation. Please like the video and follow the channel. Yeah. And if you would like to give any presentation, you're welcome to contact me as well, and we'll see how we can schedule a presentation at what time and so on. So thank you very much, and see you at next meeting, next video, whatever. Thank you. Bye-bye.
Thank you very much, everyone. Good night.